The exam might have not gone well. The exams are up here. If you're just coming in, just grab yours right here. I just finished grading these like literally 5 minutes before I came up here. So I have not recorded the grades. I don't know what you got. So I need you can look at them now, but I'll need you to hand those back in. Of course, don't write on them, don't change anything. So if you want to know how I'm going to calculate your grade, I'm just going to add up all the points that I took off. So if you go and you read through and it says, -5, -4, and you just add all those up, let's say you had -31, you would take 110 and subtract 31, and that would give you a number, and then you take that number divided by 1.1, and that's your grade. So there's 11 problems worth 10 points each. It's 110 points possible. Make sense? Yeah? Kind of? No?
Well, why divide by 1?
You can divide by 110, but then you get 0.7182. So make it 1.1 instead of 110. It converts it over to a percentage. So basically multiplying by 100. Yeah. You got it? Okay. All right. So it's hard when I grade these. The way I grade them, I grade everyone's page 1, everyone's page 2, everyone's page 3, and I just kind of like go through it. So as I'm grading, I really don't know whose I'm grading. And then at the end, it's hard for me to tell how y'all did as a class. I can tell you that my gut is that it wasn't good. That was the gut. Now I know I do have students that did do well, but my gut instinct is that a lot of students struggle because I was taking a lot of points off. And when that happens, I get that feeling. So I don't know, I'll look at the average, the class average and everything later. Any comments? My intention today is to go through 8.3, which is the section we skipped, cover that, and if I have time, which I think I will have time at the end, I want to go through the exam. If a student did well on the exam, I'm not going to force them to stay here and listen to me go through it. But I think for a majority of you, you're going to want to maybe see how these problems were supposed to be done. Okay? So I'll let you decide that for yourself if you want to stay or not. But if you leave, I'm expecting that you at least passed. All right? So without further ado, let's get into this. I don't know. Yeah, I have no idea what the class average is. I have no idea how many A's, B's, C's, D's, F's. I have no idea. I know that I believe the highest grade was 105. And I know that there was at least another one that was 100, and then a couple of others that were in the 90s. So I know that we did have students do well, but then like I said, I have a feeling that there's a larger group that didn't do as well. All right, 8.3 is where we're going to start off here. Yes, I'm going to actually go through the exam. But we have to get through this first. Okay, so here's what I'm going to ask that you do. Take your exams, put them away. Okay, I don't want you going through them right now because I will talk about them at the end, all right? And focus your attention on what's going on up here. All right, now, I've told you, I think I've said it several times, that I teach the calculus sequence a majority of the time, Cal 1, Cal 2, Cal 3. So it's very easy for me to be able to look back at pre-cal and say, what are the things that you need from here that you're going to use in calculus. And my top 2 topics for what you need from pre-cal are, you better know your unit circle, which means you better be able to establish all the basic trig functions at the common angles, and you better be able to solve trigonometric equations. Those are like the big topics. Now, of course, everything else you need to know, but these 2, they just kind of pop up, and usually when I get to them in calculus, I can tell the students who did well in pre-cal versus the ones who struggled. So I guess what I'm saying is, like, this is an asterisk topic. It's important. I like the fact that we separated it from the test, because now we can look at it like fresh start. We're going to be solving equations. That's what we're going to be doing. But these equations are going to be involve trigonometric functions in them. So our standard, when it comes to solving equations, we have our history of equations. We have like linear equations, like, I don't know, 3x plus 5 equals 2 times x plus 1. We could say solve that for x. That's a linear equation. You distribute through, you try and get x by itself on one side of the equation. All right? What other types of equations can we solve? Those are linear. Quadratic equations, right? So we have quadratic. And the method for solving quadratic equations is slightly different than linear equations. That's an example of a quadratic equation. With linear equations, we try and isolate x. We try and get x by itself on one side of the equation. With quadratics, do y'all remember what you need to do? You get everything equal to 0. So you try and move everything to one side. And then once you get everything to one side, so I'm going to bring over that 5x and that 1. Once you're here, now you pretty much have like 2 options. You either factor the left side, if it factors, or if all else fails, quadratic formula. Those are your 2 basic attacks. And then in 1414, you should have studied, higher order, like polynomial equations. That's where you start getting higher powers of x. And you've got things like synthetic division. That sound familiar? You've got all these different techniques there. And then there's even like rational equations. I'll give you an example of a rational equation. 3x over x plus 1 equals 4 plus 4 over x minus 2. That's an example of a rational equation because it's ratios. You've got x's in there. So for this one, anyone remember how to do something like that? Yeah, I know, like you learn it at one time and then it all goes away, but we need to be able to... What I'm giving you right now are the things that I would assume you could do. Like if you went back and reviewed it, you could do this. These, you get a common denominator, multiply both sides of the equation by the least common denominator. So you're clearing your fractions and then you continue through. So these are the types of equations that we can handle right now, theoretically. And now we're introducing a new type of equation, which is equations that involve trig functions. So let's just get right into it. Let's take a look at this example. We have 2 sine, I'm going to use x, 2 sine x minus 1 equals 0. And the instructions here are to solve. So just like all of these equations over here, when you say solve an equation, you're saying find me the values of x which make these true, right? Like what do I plug in here for x and here for x to maintain the equality here? That's what all of these are asking you to do. So over here, we're saying what x do I plug in to make this equation true? So out of all those equations over there, which does this look the most like right now? Linear, right? You could almost like just squint your eyes a little bit, and like if you call that, let's say u, then this kind of looks like 2u minus 1 equals 0, doesn't it? Like if you just replace that entire sine x with u, this looks linear, right? And that's how we're going to go about it. We're going to try and treat it like a linear equation. We're going to try and isolate isolate the sine x part. Try and get it by itself. So how would you do that if you want to isolate, get the sine x by itself? What would be your first step? Move the 1 over. So add 1 to both sides, right? So you would go 2 sine x equals 1, and then you would say divide by 2, right? Divide both sides by 2 because that's multiplication. So you're going to undo that by dividing by 2, and you get sine x is a half. Okay. So we've isolated the variable just like we would have done here. Now comes the part where your familiarity with the unit circle and all that stuff I've been trying to stress comes into play. Can you tell me my solutions here, right? X, are they angles? Are they numbers? What are they? They're angles because we're plugging them into a sine function, right? Sine functions take in angles and spit out numbers. So this is saying what angle do you plug into the sine function to get 1/2? Which really means where on the unit circle is the y-coordinate 1/2. That's what this is saying, right? So now we have to come over here and I'm going to draw a little unit circle. I'm trying to figure out where the y-coordinate on the unit circle is 1/2, and that occurs here and here. And what are those two angles? This one is pi over 6, and this angle is 5 pi over 6, right? So would you agree that x would have to be pi over 6 or 5 pi over 6, and this would work? Yes? But those aren't the only solutions, because not only could I use pi over 6, I could also go all the way around and come back here, and it would still give me the same y-coordinate, wouldn't it? And I could go around twice. I could go around 3 times, right? So how can I represent this dot, pi over 6, but all infinite possibilities? Plus n2 pi or 2 pi n, right? So to get back to this point, we have to go all the way around. Notice we cannot jump over to that point, right? We can't, I mean, we could, but then whatever we jump by, if we try and jump again by that much, we would not land on one of these dots. Now, I gave you a quiz in class on this. We talked about it again afterward, and I've tried to stress to you the importance of this. Do you see why kind of now it's going to come into play? All right, so what can you tell me about my solutions x? My x's, right, those x's have to be pi over 6 plus, you said n times 2 pi, right? I'm going to write 2 pi n. It doesn't matter if you put the n in front, but we usually throw the n in the back. Or, right, or x has to be the other angle, which is this one, and then you have to be able to jump all the way back around to it, right? So 5 pi over 6 plus 2 pi n. Any questions? How many answers are there? Yeah, 2, but I mean, literally, how many are there? Infinitely many answers, right? How would I get, if I asked you to give me a list of 10 of them, how could you get them?
Plug in n.
Okay, plug in what for n? I'm going to replace n with integers. I'm going to first replace n with 0. Then I'm going to replace n with 1. Then 2. Then 3. Then 4. And every single time I do that, I'm going to get answers, different answers, right? So I'd like for us right now to actually list out a couple of answers from each list, from each of those sets, just so we can get a feel for what's happening. So here's one way you could do this. If we want specific answers, right? What I could do is just start choosing different values for n. So let's start with n being 0. If n is 0, we'll make almost like a little table here. If n is 0, what do I get from this one? Just the pi over 6, right? 0 here kills that off, you just get pi over 6. What do I get from this one if I let n be 0? Kills that off, you get 5 pi over 6. Okay, so that makes sense. It makes sense that we should get the two answers that we started with, right? Now let's let n be 1. We're going to have a whole set two more answers now, right? Now when I do n is 1, I'm going to do some scratch work here on the side. When I do n is 1, I've got to do it on both of these, right? So the first one becomes x equals pi over 6 plus 2 pi times 1, which is just 2 pi, right? And to put those two together, I have to have a common denominator. So I multiply this 2, I look at it as 2 over 1. I multiply top and bottom here by 6. So I get pi over 6 plus 12 pi over 6. They have the same denominator, add them together, 13 pi over 6. And that's what I would get if I let n be 1, 13 pi over 6. That is another solution. Now I'd have to let n be 1 on the other one, right? So x equals 5 pi over 6 plus 2 pi, but that equals 5 pi over 6 plus common denominator again, 12 pi over 6, which is 17 pi over 6. So that's another solution, 17 pi over 6. And then I let n be 2, right? And that would give me another list, another set of numbers. And I could do that for every integer. Remember, n is an integer in these problems. N is an integer. 0, 1, 2, 3, 4, 5 forever. And also negative 1, negative 2, negative 3, negative 4, negative 5, all the way forever. Now, I've given us some positive values of n, but we should probably practice with some negatives just to have them. But I want to do another n equals positive integers, so let's go 2. So if n is 2, how are things going to change here? It's still these two, right? But then I have replaced this with 2, so it would be what? 2 times pi times 2 would be 4 pi here, and then this one would be also 4 pi. You'll get what I'm doing? And then common denominator again. So if I got a common denominator, pi over 6 plus 24 pi over 6. And then this one, let me do this one right now, 5 pi over 6 plus 24 pi over 6. And what are our two results here? 25 pi over 6 and 29 pi over 6. All right? Now, it may seem like I'm kind of being redundant here and like you get it, right? But if n is 3, then I would do it again, right? And the part that kind of gets a little tedious is the fact that every single time I do an n, I have to get a common denominator. Right? This part right here, I have to get the common denominator, common denominator, common denominator. We can actually do something to avoid that, where we don't have to get the common denominator. But it goes back to this right here. Remember, these were our two general answers, right? This is what I used to construct all this. I want to go back and revisit those for a second, because I don't like getting the common denominators. Let's look at this one right here. X equals pi over 6 plus 2 pi n. Let's get a common denominator now, here. So what would I do if this is like 2 pi n over 1? Multiply top and bottom by 6. So you get pi over 6 plus 12 pi n over 6, right? Now, can we put those together? Do they have the same denominator? Yes. But you cannot put pi plus 12 pi n because they're not like terms. So what I could do is this. Pi plus 12 pi n over 6, right? That I could do. And I'm just going to box that and leave it there for a second. And then I do the exact same thing for the other one. This is a little bit more work to do this, but it pays off in the end. 5 pi over 6 plus 12 pi n over 6, which is 5 pi plus 12 pi n over 6. So same story, get a common denominator, and you get that. Go with me on that? Okay, now check out what's nice about this. I'm going to shut this door. I don't know why. Open doors make me nervous. Okay, if I had gotten my answers in the very beginning here, before I made my table, and I converted them to this, watch how fast I can create this list right here. Okay? First, if n is 0, what is this? Pi over 6, right? What if n is, so that's this one. What if n is 1? Pi plus 12 pi is 13 pi over 6. Now I've got this one. Now n is 2. 12 times pi times 2 is 24 pi plus pi, that's 25 pi over 6. Now I've got this one. You see how fast I work through that? What about the next one? If n is 3, 36 plus 1, so 37 pi over 6. That's my next one. What would this one be?
41.
41. So you plug in, you're plugging in 3 here, and you're getting 36, and then 5, that's 41. 41 pi over 6. Let's try a negative n. What if n is negative 1? So replace this with negative 1. This becomes pi minus 12 pi, which is negative 11 pi. So we've got negative 11 pi over 6. And if I replace this n with negative 1, I get 5 pi minus 12 pi, negative 7 pi over 6. And you see, I could just sit here all day long just plugging in n's, right? So I hope I've sold you a little bit on the idea of getting your general solutions with the common denominator. If you're going to go find a list of numbers, this is the most efficient way to do it. If you're not asked for a list and you're just asked to find the general solutions, you can just leave it like this. This is fine. All right.
Professor,
yes.
when you take 1, 2, 3, or if you take negative 1, is that like obvious that the difference is going to be a plus 12 in the numerator and negative 12 in the, if we go backwards from 0? Or do we, or is there a possibility that it might change in the end?
It's not going to change. It's never going to change. The question was, can we just use the fact that there's a pattern here that keeps going up by 12? Right? And that way, if you went backwards, it would go down by 12, and that would have given you this. That is guaranteed because the only thing that's changing are all multiples of 12. So every time you move, it's changing by 12, by 12, by 12, by 12. So you could use that pattern, yes. All right, let's try something a little different. Let's try a new equation. We've got 2 cosine, I'm going to use theta instead of x this time, plus the square root, yeah, I already did it, plus the square root of 3 equals 0. So does that look like a linear equation, quadratic equation, polynomial, rational? If you replace this cosine here with a u, would this look linear or quadratic or polynomial or rational? Still linear, right? This would look like 2u plus some weird number, but it's still just a number, right? This is just a bunch of constants, and then you'd have something that's just to the first power. So we isolate the cosine theta again, get it by itself. So subtract the root 3 from both sides. And then divide both sides by 2. And that, fortunately for us, should be something we recognize. That is saying to us, where on the unit circle is the x-coordinate negative root 3 over 2? Where is the x-coordinate negative root 3 over 2? Here and here. What are those two angles? 5 pi over 6, and 7 pi over 6. Okay? So that means that in order for this equation to be true, I must let this angle right here, right? That angle must be one of those two. And then how do we get all the other solutions? How do I get all the solutions that are equivalent to this one? I've got to go all the way back around to it, right? So I add 2 pi n again. How do I get all the ones here? Go all the way back around again. So I'm going to write down that theta must be 5 pi over 6 plus 2 pi n, or theta must be 7 pi over 6 plus 2 pi n. Understand? Any questions?
Do we have to put both the 5 pi over 6 and the 7?
Yes, because if you just do the 5 pi over 6, then if you go all the way around, you will have a solution, but you're missing an entire infinite set of solutions still. Now that would be it. If all you were asked to do here is solve this, you'd be done. All right? So I'm going to add one additional element to this. All right? I want us now, we're done if that's all we were asked to do. If the instructions said find solutions in the interval -4 pi to 4 pi. Give me just the answers that are inside here. All right? Well, that means I need a list. And I need to create a list until I have every single answer that lives in here. Every one. So if we're going to do a list, we should probably do a common denominator on those, right? Let's do that. So I'm first going to start with this answer. If I get a common denominator, it's going to be 12 pi n again over 6, which should be 5 pi plus 12 pi n over 6. That's one of my general solutions. The other one, I'll save us the writing of it. It should just be what? 7 pi plus 12 pi n over 6. Look, it's not always going to be 6, okay? It has been for the first two examples, but it's not always going to be 6 on the bottom. All right, let's start creating a list. Notice that we want our answers, right? These are thetas in here. These are our thetas. We need our answers to be both positive and negative, right? So I'm going to have to let n go both ways here. So let's start doing it. All right, let's go with if n is 0 first. If n is 0, tell me what answers I get. I'm not going to do a table this time. I mean, they're cute, but you know, we don't have to be cuter to do this. What do we get? 5 pi over 6. That's what we get from the first one. And then what do we get from the second one? 7 pi over 6. So those are my two solutions if I plug in 0 for this and 0 for this. All right, now let's let n be 1. n is 1. Off the first one, 17 pi over 6. Off of this one, 19 pi over 6. 17 pi over 6, and then 19 pi over 6. When am I going to stop? When I get to 4 pi or past 4 pi. How do I know if I'm there? Are either of these past 4 pi? Yes or no? Why not? No, why not?
But if you divide 17 by 6, you get 2 point something.
Okay, yeah, so you need to look at the coefficient here. This 17 over 6. What's 17 divided by 6?
2.9, 2.8.
Yeah, it's almost 3, isn't it? Because 18 divided by 6 would be 3. That number right there is still smaller than 3. We need to go out to 4 pi, so we need the ratio out front to get past 4. So let's go with n equals 2. What happens when n is 2? 24 pi plus 5 pi is 29 pi over 6. And then what would the other one be? Let's just do them both right now.
31 pi over 6.
31 pi over 6. Any questions on where I'm getting these? And now let's just check. Is this coefficient here still smaller than 4? It is not. 29 divided by 6 is bigger than 4, which means we are now outside of 4 pi, so we do not want to include that. And then 31 over 6 is also bigger than 4, right? So we do not want to include that. So do I need to do n equals 3? No, because I know everything now is going to be bigger. So I'm done with the positives. I have, what, 1, 2, 3, 4 positive answers? And now let's get the negative ones. So now just start plugging in negatives. Negative 1. If I plug in negative 1, we get
Negative 7 pi over 6.
negative 7 pi over 6 and
Negative 5 pi.
negative 5 pi over 6. Are those both within here? Yeah, because if you take negative 7 and divide it by 6, it's just barely over 1, right? So you're good. And this one is still less than 1. 5 over 6 is less than 1. So that's a good one. Let's go with another one. N equals 2.
Negative 19 pi over 6.
Negative 19 pi over 6.
Negative 17.
Negative 17 pi over 6. Everyone agree? Does anybody have a question on what I'm doing or like where the heck those numbers are coming from? Let's just check them. 19 divided by 6 is still smaller than 4, right? And 17 divided by 6 is still smaller than 4. So these two are good. Let's try n equals 3. Now, negative 3. Oops, this should have been negative here. I apologize. This should be negative. Look, did n equals 3 work up here? No. That does not mean, look, n equals 2 didn't work, right? N equals negative 2 did. So you cannot say, okay, if you go out to this, if you can only go out 1 here, then you only have to go backwards 1. You cannot do that. You have to check them. Am I making sense? I wish there was some symmetry to that where you just had, once you check the positives, that's the same thing. You have to check the negatives, but unfortunately, it's not the case. All right, let's do negative 3. Negative 3 right here is negative 36 pi plus 5 pi. That's negative 31 pi over 6. And that's bigger than negative 4, isn't it? So, when we say bigger than negative 4, I shouldn't say that. It's to the left of negative 4 pi. It's outside. It's no good, right? Smaller, yeah. It's smaller because it's to the left. And then the next one, what was the next one? Negative 29 pi over 6. Is that outside? Yeah, that's outside also. So that's it. We're done. So your answer is 1, 2, 3, 4, 5, 6, 7, 8. Those are the 8 solutions to that equation that exist within the interval negative 4 pi to 4 pi. So now that we've been through 2 of these now, would you agree that the general solution is almost easier to get than if you restrict it? Like if you say, just look between here and here, and you have to come up with this list, this is more work, isn't it? Yeah. Okay. Most of the homework problems want you to find all the solutions on an interval. So you'll be having to do this. On the test, a lot of the problems that I'll give you, I just want general solutions. Because my idea is if you can find the general solution, you can find all these without, having to go through it all. But you will have to do some, just not the whole test. All right, let's step it up a little bit here. I'm going to change something on this problem. It's going to be kind of subtle, but how about this next example? Let's find solutions on negative 2 pi to 2 pi. So I just want us looking between negative 2 pi and 2 pi for the answers, the solutions to this equation. Tangent 3 theta equals, plus 1 equals 0. All right. Does anyone see the big difference in this problem? Instead of theta, what do I have? 3 theta. Remember what I called this thing, the thing that goes inside the trig function? The argument, right? The argument in the previous 2 examples was just x or theta, right? Now it's 3 theta. That makes a huge difference in your answers. Huge. Well, let's still try and work with this like a linear equation. Let's move the 1 to the other side. Let's say tangent theta, 3 theta is negative 1. So that means that I'm trying to find the angle that when I multiply by 3 and plug it into tangent, I get negative 1. So where does tangent spit out negative 1? Where does that happen? Tangent spits out negative 1 at 3 pi over 4 and this one, 7 pi over 4. Why is negative 1 there? Why is tangent negative 1 there? Because sine and cosine, the x and the y coordinates are the same except they're off by a sign, right? So when you take the ratio of the 2, you get negative 1. We clear? Okay, here's the part you have to pay really close attention to. At this point, you are going to set the argument of the function equal to the general solutions. So instead of saying theta needs to be equal to that, I'm going to say 3 theta needs to be equal to the general solution. So let's look at this. 3 theta must be equal to what? You said this one was 3 pi over 4. You said this one was 7 pi over 4, right? So can I do 2 lists? Can I do 3 pi over 4 and then go all the way back around to it? I could do that, right? I could. And then I could do 7 pi over 4 and then go all the way back around. But there's a more efficient way. Because these are directly across from each other, I can start at 3 pi over 4 and jump just straight across and then straight back and then straight back and then straight back. So what could I write for my general solution here? 3 pi over 4 plus just n pi, or pi n, you can flip it. But it's not 2 pi because we're not going all the way around, right? It's just a single pi, which is a half rotation. Okay, is that clear?
So even if you did like 2 pi n, would that be wrong, or would that be
2 pi n would not be wrong here, so long as you then wrote 3 theta or 3 theta equals 7 pi over 4 plus 2 pi n. So you'd either need 2 separate general solutions with an or between them, or you could do this one general solution that knocks them both out at one time. So I'd prefer this one. I mean, I would do this one. If you on a test did 2 separate ones, I wouldn't care. Although I would say, well, they don't see the value of the efficiency of doing it in one. We good? Now, I said that we should probably get a common denominator, right? Not yet. What should I do first? Let's get that 3 out of there. This is the big step, the change from the previous problem. Because our argument is 3 theta, not just theta, we're going to divide this 3 out first. And when we divide it, we're going to get 3 pi over 12, because we're dividing this by 3, plus pi n, I don't know why I switched the order, over 3. So when you divide that by 3, it's this. When you divide this by 3, it's this. Now, I could have just canceled the 3's and reduced that fraction. I'm going to do that on the next step. But is everyone clear what I did? Okay. Now, this is, theta is just pi over 4, right? Plus pi n, or n pi over 3.
leave it that way?
Yeah, I'm going to go back. It's going to go back to 12 in a second anyway, all right, because I need to get a common denominator now. So to get a common denominator, my common denominator should be a 12. So I'm going to multiply top and bottom here by 3 and top and bottom here by 4. So theta should be 3 pi over 12. See, I'm back to where I was. And this one is now 4 pi n over 12. So I multiply top and bottom here by 4, top and bottom here by 3. And now I can put them together to get a really nice general solution, 3 pi plus 4 pi n over 12. Is that 7 pi n? No, you may not put those together, right? You cannot put those together. They both have to have an n in them for you to say 7 pi n. This right here is our general solution. That's the general. This will give us all the infinitely many solutions there are to this equation. But I only want the ones between negative 2 pi and 2 pi. So now I start spitting out the list. And we'll plug in n is 0 first. If n is 0, what do we get? Yeah, this is gone, right? So we just get 3 pi over 12, which is really just pi over 4. So we get pi over 4. And that's it, right? That's it. When n is 0, that's all we get, one answer. Now, n is 1. When n is 1, we get 7 pi over 12. Are we still inside of here? Yeah, we can only go out to 2 pi, so I need the ratio of these two numbers to stay smaller than 2. Right now we're good. N equals 2. 11 pi over 12? Are we still good? Yes? These keep jumping up, but notice they're not jumping up by the same amount each time. They're not because our formula is taking care of 2 at the same time. It doesn't work. I'm just saying, plug in the ends. Don't try and find a pattern. Just plug in the ends. 3 goes in, 12, 15? 15 pi over 12. We can reduce that, can't we? 3 goes into both of those, so 5 pi over 4. Are we still smaller than 2 pi?
Yeah.
Yes. 5 over 4 is 1.25, so we're still smaller. And we keep going. N is 4. 19 pi over 12. Are we still smaller?
Yeah.
Yes. Okay, n equals 5. 23 pi over 12. Are we still smaller than 2 pi?
Yeah.
Yes. N is 6. I think this is where we're going to bust out here. 27 pi over 12. And 27 over 12 is bigger than 2. So we're done. We're going to eliminate this answer. So we're done with the positive answers. There are 1, 2, 3, 4, 5, 6 positive solutions to that equation. And now we go get the negative ones. All right, n is negative 1. I just erased what I needed. Well, you have it written down, so I'll trust you. What is it? Negative pi over 4? Okay, how about n is negative 2? Negative.
Should it be negative pi over 12?
Oh, did you say 12? Sorry. 12? My apologies. What was the formula again? It was 3 pi plus 4 pi n? Yeah, all over 12. Okay, so negative 1 in here gives us negative pi over 12. Negative 2 here gives us a negative 8 plus 3, so negative 5 pi over 12. I'm going to be here for a while. Okay, next one, n is negative 3. So that's negative 12, and then plus 3 is negative 9 pi over 12. I could reduce that, but I'm not even going to. Okay, negative 4, so we're at negative 16. What is it?
Negative 13.
Negative 13 pi over 12. Still, we just barely got past negative pi, right? Because 13 over 12 is a little bit bigger than 1. So I've got to keep going. Negative 5, 20, negative 17. Pi over 12, n is negative 6. negative 21 pi over 12.
Now we're gonna cross out.
We're gonna be past it on this one. Negative 7, negative 25 pi over 12, which is too big. Everyone clear on why that's too big? Why we're outside? Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 solutions.
Sir,
Yes.
you need to put in parentheses, which is something like that,
Parentheses what?
like answers, like.
The book is going to list them out. The book is going to put a set of braces, and they're going to list all the answers like this.
So we have to.
You don't need to use a set of braces. You can just, as long as you box them, so I know where they are, like I can find them, you know. I did notice that on the test. I had a lot of trouble finding answers on some things. I saw lots of work, but I couldn't find the answers. So if you box these up, there they are. You like the general solutions? Yeah, the general solutions are a lot better, aren't they? I find in my calculus classes that a lot of students come to me and they know how to get these, but they don't know how to get the general solutions, which boggles my mind because I can't figure out how they're being taught. Because you shouldn't be able to get to these easily without having a good general solution. So I think they're being taught off of graphs how to find them or something, because I don't understand it. But yeah. All right, let's do something else. This one's going to be a little different. That hurt. How about this one? Solve this one. Cotangent of 2 theta plus pi over 2 equals 1 on the interval 0 to 2 pi. I'm going to do this, 0, 2 pi. So this, the only difference this is with me putting parentheses here is that if we get an answer, if one of our answers is 2 pi, we are not going to include it. Because this is saying only look inside of 2 pi and past 0. All right, so what do you think here?
For the angle where cotangent is 1.
Yes, this is saying where is cotangent 1, right? Don't try and move this over to the other side. You can't. It's trapped inside the cotangent function. It's part of the argument. So we're just really saying to ourselves, where is cotangent 1? Well, cotangent is the reciprocal of tangent. It's just tangent flipped, right? So this is really saying where is tangent 1? So that's going to happen here at pi over 4 and also at, what is that? 5 pi over 4. Now they're directly across from one another, right? So this is a good thing. We can jump around from one to the other. So what we need now is to set the what equal to what here?
Pi over 4 plus n pi.
So the entire argument, right? We're going to set the entire argument 2 theta plus pi over 2 equal to, you got to create your general solution. You said pi over 4 plus what? N pi. So again, the n pi, we're going to start at the pi over 4. We're going to jump around by pi's. Pi, pi, pi. Could I have started at 5 pi over 4? Could I have put 5 pi over 4 right here instead?
Yeah.
Yes. That won't change it because I'm still going to jump around. And because n is allowed to be negative, you can go both directions. So we're all good. All right. Now what?
Subtract pi over 2.
We need to isolate theta. So we're going to subtract pi over 2 from both sides. So when I take pi over 4, I'm going to subtract pi over 2 from it. And then I still have plus n pi here. Notice I can't do anything. Like the pi over 2, when I subtract it, has no impact on this because this is n pi. They're not like terms, right? You cannot, apples and oranges, we can't put these together. So this right here, you'd have to get a common denominator, which would be 4. So to get a 4 down here, you have to multiply top and bottom by 2. So this will become a 2 up here, and this will become a 4 down here. So you subtract and you get negative pi over 4. So here's where we are. We have 2 theta equals negative pi over 4 plus n pi. Now divide by 2. We'll divide everything by 2, both sides. So theta is negative pi over 8 plus n pi over 2. And yeah, we're going to put them together, right? We're going to get a common denominator right now. So I need to hit this top and bottom right here by 4. Negative pi over 8 plus 4 pi n over 8. That's just getting my denominators the same. And now let's place them together. I'm going to write it like this. I'm going to write 4 pi n minus pi all over 8. Just because this was a negative, this is positive, so I just put it in that order. There's our general solution. And now, start plugging in n's, right? We have to stay bigger than 0 and less than 2 pi. So let's start at 0. That's always the best place to start at. N equals 0. What do we get? Negative pi over 8. Nope, we don't want that one, right? Because that's outside of 0, 2 pi. It's a negative answer. So I don't need to check negative 1, right? If I check negative 1, it's going to give me more negative. I don't need it. So let's go to n equals 1. 3 pi over 8. We definitely have that, don't we? We definitely have that. That's within here. 0, 2 pi, sorry. Okay, n is 2. 7 pi over 8. N is 3. 11 pi over 8.
Sir, if you're using from 3 to 2 pi, I mean, we could have solutions from half, 3, 4, 2, like.
If we're doing, say again?
Like if you're using solutions to look at from 3 to 2 pi, we could use half, we could use a quarter, we could use something else. I mean, would that work too?
A half? I'm not sure where you're getting a half from.
1, 2, 3, 4, right?
Oh, can we look at a half? No. No. Because what you have to remember what the n represents. The n is, we started out, well, we have to start when we wrote it the first time. It was pi over 4 plus pi n, right? That's what we said all of our solutions look like. So what we meant by that is that if we started pi over 4, then what we could do to get back here is add a single rotation of pi. That would put us here. Two rotations of pi, which would get us here. 3 rotations of pi, 4. So if you say 1.5, then what you're actually doing is you're saying there's 1 pi, but here's a half pi. You'd be down here. You're no longer on these two. So that's why it's important to understand that n has to be an integer. Does that address your question? Okay. Where does this thing stop? So 4 is 8 minus 7. Wait a minute. Hold on. Did I miss one here? 4, 16. This is 15 pi over 8, right? That's pretty darn close. And then you go here, you bust out, right? It's 19 pi over 8. Too big. What do y'all think of this? It's all right? You sure? How about this one? Cosine squared of 4x minus 1/4 equals 0. Notice something different here?
Well, cosine squared.
We got a cosine squared here, right? We've got a cosine squared. It's the first time we've seen this. But let's not get too freaked out about it.
Can we change it by identity?
You could change this. You could use the identity, which would take you to 1 minus sine squared. But that's really not going to do a lot. We could work with that and wind up doing the same exact thing we're going to do here. How about this? How about we move the 1/4 to the other side? Is that all right with you? Okay. Now I know this is a quadratic, but if you squint your eyes hard enough, do you kind of see that it looks like this? It's like the cosine is being squared, right? So it's like something squared minus 1/4. What I want you to see is that if you move the 1/4 over to the other side, and then take the square root on both sides, you can get the u by itself, can't you? That's what I'm about to do. So this is a quadratic, but it's a special type of quadratic. It does not have the middle term. It doesn't have the u term. It has u squared, but it's missing the u. Does this sound familiar to you? When you're missing the u term in a quadratic, you do this technique. You don't have to do the factoring of the quadratic formula. So I'm going to move that over. And now I'm going to take the square root. And when I take the square root,
Plus minus.
plus or minus. You have to do plus or minus. So square root of the left side equals plus or minus the square root of 1/4. And what's the square root of 1/4? 1/2, right? So the left side becomes cosine 4x. Wait, is it not 2x now because I took the square root? No, you're taking the square root, the squared here and the square root are the things that cancel each other out. You're not taking the square root of the 4 inside. And then this is going to be plus or minus 1/2. So what am I saying to myself now?
You have two equations.
Okay, I do have two equations. I have cosine 4x is 1/2 and cosine of 4x is negative 1/2. So in terms of the unit circle, what is that really asking me to identify? Where's the x coordinate? A half and a negative half. So if I draw this on a circle, let's start with where is the x coordinate positive 1/2? Pi over 3 and that one right there? 5 pi over 3. The x coordinate is 1/2 at both of those points. Where is it negative 1/2? 2 pi over 3 and here. Yep. Now these two are directly across from one another, aren't they? And these two are directly across from one another also. So I'm going to have two sets of answers, right? It's going to be this or this. But so instead of having 4 separate answers, I'm going to have an answer that takes care of these two at one time and an answer that takes care of these two at one time. This is starting to become messy. So I'm going to, what are my equations I'm setting up? I forgot. What am I setting up here now? 4x equals, so let's start at this one right here. This angle right here was pi over 3. And then you want to start there, go directly across, and then come back, and then directly across, come back. So plus what? And pi? Or you could have that 4x is this one right here, which was 2 pi over 3.